into this complete. Okay, here you go. Today is 25th of February 2026. That's Physics 7. And we start recording a little bit late. Okay. And one more students coming here. But I'll try to review quickly what we did so far. So it stay recorded in the cloud, right? The first thing that I want to tell you is about, and that's good for those who arrived a little bit late. The first thing I want to tell you about is the solution of the electric flux, okay? That's the equation for the electric flux, the electric field times the area vector times the cosine between the vectors of the electric field and the area vector, cosine of the angle between the electric field and the area vector. That's what the very definition of electric flux is. We are going to use this idea of the electric flux in one of the laws of electricity that's called Gauss's law. Okay, and we did this example. Let a point charge of charge Q find the electric flux going through a spherical surface of radius r centered at the charge. We did that last time, and the configuration, the geometrical configuration is exactly this one here, right? Here you go. Here is what we call a Gaussian surface, an imaginary surface that's surrounding this electric charge, and the center of this Gaussian surface, this imaginary surface, coincides with the position of the electric charge. Okay, the center of the Gaussian surface coincides with the point where the charge is located. Okay, and we are going to this is not a planar geometry. This is a spherical geometry type of problem. Previously, we did a planar geometry type of problem, right? If you're here last time. So here you go. We start to find the electric flux going through this spherical surface of radius r. That's centered on the charge. So how do we do? Okay, first we identify the angle between the electric field and the area vector. Going back here to this illustration, we already know that the electric field radiates away from this point charge, right? And because this surface area, the center of the surface area is centered at the charge, the electric field is going to be normal, exactly normal to this spherical surface. Okay? Normal means it makes an angle of 90 degrees with respect to a plane that's tangent to this surface. So the electric field at this point is going to make an angle of 90 degrees with the normal of the surface, 90 degrees here, 90 degrees here, and so on. Okay? And then, here you go. Here's the electric field. 2 points along the surface. Okay? And for this specific geometry, the area vector coincides with the direction of the electric field as well. The area vector is the red arrows that you see right in here. Let me put it right in here, right? At this point right here, the area vector is going to point exactly in the same direction as the electric field. Okay? Similarly, at this point right in here, the area vector will also point in the same direction of the electric field. They don't have necessarily the same lengths, because those are two different quantities. Okay? And because the area vector and the electric field points exactly in the same direction, right? The angle between those fields, those vectors, are going to be 0 degrees. Now, the area of that surface is 4 pi square, 4 pi r square, because we are talking about the area of a spherical surface. And finally, the electric field, since it's the electric field of a point charge, it should be written down as kq over r square, okay? R square. If you remember last time when we were here, I wrote down kq over r. I was writing the potential, not the electric field, okay? So it's r squared. That's what I want to point out to you all. And once you have kq over r squared, this r squared cancel out with the r squared, and the electric flux is just a constant. What we have here is the solid angle for pi, the solid angle around the whole space, and then the K2 parameter, which is, K, the universal constant, and Q, the charge, okay? The charge that's being surrounded by the imaginary surface. Okay, and what else? What else I said, right? That didn't get recorded in the first 20 minutes of class, 25 minutes of class, right? So if we are going to now calculate the flux through the same spherical surface, but positioned at a different spot, the center now is shifted, in this case, to the left, okay? The electric flux is still going to be the same, okay? So what if we were to repeat the problem, the previous problem, for a spherical surface with its center, whose center is displaced from the point charge, right? Just like you see in the illustration below. We still would be able to calculate the electric flux because we have a single charge inside that, okay? And that's where Gauss's law enters into focus here, okay? What Gauss's law states? Gauss's law, let me see, we should be able to calculate because of Gauss's law. Let me, Gauss's law, which is stated in the following form. I didn't put the format of the Gauss's law, but I'm going to put it right now, okay? Here you go. The format of Gauss's law is the following. It's going to be only format. The electric flux with one important detail. I'm going to write down here. And the Gauss's law is given by the electric flux through, here you go, a closed surface. Here you go. I'm going to put it here, closed surface. Is going to be given by what? 4 pi k times the electric charge enclosed by this surface, okay? So even if our surface is displaced like that, the electric flux would still be the same through this surface. But don't forget, this Gauss law applies only to a closed surface. Notice that this Gauss law applies only to a closed surface. Okay. So the value of the Gauss law still would be the same as we got before, even though we have a different surface. Okay. So the result still would be, so the result still would be as before. For pi kq. Okay, now why am I saying that? Okay, am I saying that because of the following? In addition to that, and I mentioned that before, Gauss's law uses the concept of the electric flux to determine the electric field of a given charge distribution. Okay, that's why we introduce you to the Gauss's law. Gauss's law is just, Gauss's law is just another format of Coulomb's law. But is a more convenient, even though it's another format of Coulomb's law, it's still a more convenient format to determine the E field. So let me see, just a measure of the number of electric field lines passing through a given. Yeah, that's right. That's how you should interpret that. That's right. Here you go. Okay, so here you go. The electric flux is related to the number of electric field lines passing through the surface. Okay, the more electric field lines passing through the surface, the larger the electric field is. Okay, in this illustration, I did 1, 2, 3, 4 electric field lines only, right? But if I were to increase the number of electric field lines, what I would be saying? I would be saying that not only the electric field will be stronger, but the electric flux will be stronger as well. That's a geometrical interpretation of the electric flux. Okay, Jeremy? And in addition to that, let's say, notice that Gauss' law applies only to a closed surface. So the result still would be as before. In addition to that, Gauss's law uses the concept of the electric flux to determine the electric field of a given charge distribution. So Gauss's law is just another format of Coulomb's law, but it's a more convenient format. It's easier. It allows, okay, since it allows the determination of the E field in a simpler way, using a simpler technique, mathematical technique, okay? Mathematical technique. However, that's the plus of Gauss's law, okay? That is its plus, and that is its plus, okay? On the other hand, since it's a simpler technique, because it is a simpler technique, it cannot solve all problems, okay? But only those problems that have symmetry, geometrical symmetry. And now we go back to that case of the sphere, that is displaced from which center is displaced from the electric charge, okay? Even though we can calculate the electric flux, okay? So in the case below, even though we can find out the electric flux rather easily, you will see that this geometrical configuration does not allow for the solution of the electric field alone, okay? Of the electric field alone. On this surface, electric field alone on this surface, right? So so it's two things that are two different things, right? One is the electric flux, and the other is the electric field. We use the electric flux to find the electric field using Gauss's law, but not every problem can be solved using Gauss's law. Okay, and okay, now we recorded, right, what we missed. And let's go now to the lab activity. Instructions for lab today. You should have your spreadsheet in your group folder right now, right? You must have your spreadsheet in your group folder right now. It should be right now, right? Let me put it. Let me put that as the first item here. Huh? Today's lab spreadsheet must be labeled according to the following format: P07L01G, two-digit group number, 01, 02, all the way up to 18, right? Download your spreadsheet, your lab, instead of group spreadsheet, let's put lab spreadsheet to your hard drive. Don't try to open it directly from the cloud. You must download it to your hard drive first, and then open it. Open the spreadsheet directly from your hard drive. Make sure, make sure, right? Make sure you have, let me put something else here. Make sure you have Microsoft Excel installed in your computer, okay? Otherwise, you won't be able to open this spreadsheet. Everybody has Microsoft Excel? If you don't answer, I'm going to assume that everybody has. Okay. Okay, good. Thank you, Susan. Okay, so once you open the spreadsheet, I'm going to open one of the spreadsheets here in my computer. Some of the students who took my Physics 6 course, they already know how to handle that, right? But there is a large number of you who didn't take Physics 6 with me. So I'll have to walk you through what you have to do, okay? One student, what time is that? 3:20. Okay, can go for another half an hour, right? 20 minutes, 30 minutes before we take our break. Okay, make sure you write down your group number here. You have, see, electric field 1. Here is the data of your experiments that were collected by another group of students in the past. This is actual data, okay? This is actual data that was collected by other students. And I'm gonna go through that for you. But first, make sure you write down your group number in the spreadsheet. Write down your group number. Here you go. Now, this one here. 5. Write down your group number in the proper cell inside your spreadsheet. And this cell is before, right? Spreadsheet. Write down your group number in the cell B4. Okay? Before. Inside your spreadsheet. Note C, right? How the spreadsheet is organized. The columns of the spreadsheet are labeled with letters A, B, C, D, E, F, G, okay? And the rows of the spreadsheet is labeled as numbers, okay? So B4 corresponds to this cell right in here, B4. In case you are not familiar with Microsoft Excel, okay? And then what else you have to do? Write down the name of each student in the following format, First, the family name, right? Family name, comma, right? And your first name, first name. Okay, so, in my case, right? If I were a student, what I would write here, I would write it Egalon, comma, Claudio, right? Family name, comma, first name. I want you to do that. If there is of course, every group has a second student. The second student should write is her name there as well. Okay, and write down the date as well. Write down the date you perform this task, right?
Where it says student one and student two, we write down our name and then our partner's name and then the date where it says the date.
Yeah, that's right. Group number, right? Group number, name of student one, name of student two, and the date. Okay,
Okay.
straightforward, right?
Okay, you said 001 for group number one.
Yeah, it should be 01, right? Right,
Oh,
01. Yeah, just correct there because I wrote down P07L. Let's see. Sorry, P07L01 G01, right? In your case, I made the mistake of writing just G1, right? So correct that for me, please, Wani.
okay.
Okay, so those are the first steps, and now we can start the experiment. Okay, what I'm going to do now, what I'm going to do now, what I'm going to do now, I will describe exactly how the experiment is performed. Okay? If someone is how the experiment is performed. And I'm gonna need another pad. Here you go. So let me show you how we perform this experiment, right? I'm gonna make a list of the equipment as well. It's 327. Let's see here. Every time that we perform an experiment, every time we perform an experiment, what we have to know, we have every time we perform an experiment, we document two things. One, the procedure, the experimental procedure, okay, and the materials used, materials slash equipment used. That's what we do. And all of that is very well documented in my labs. I have performed this lab several times. Not only I taught this lab, but I also have familiarity with the equipment used in the lab because I use the same equipment to do my own research. Okay. And the first thing that we are going to use here in this lab that you have to know, it's okay, materials slash equipment. One, we are going to use a special type of paper sold commercially. Okay. To special type of paper that allow us to make measurements to visualize the electric field of a given electrical charge configuration. Okay. The name of this paper, okay, there's a name for this paper, is resistive conductive paper. Okay. Resistive / conductive paper. The name of this paper is resistive conductive paper. Some people call it resistive paper, other people call it conductive paper. I like to call it resistive paper. I like to call it resistive paper. So we can go, it looks exactly what you see right in here. It's a black paper. Unfortunately, I don't have one of those black papers here with me, but we can check the internet so you can become familiar. Okay. It's a black paper, the size of 8.5 by 11 paper, made of, it's kind of is a carbon material, okay, that allows you to make measurements within this paper. Let's take a look at the internet so you become familiar with this paper. Let's see here, conductive paper. Conductive paper, electric field lab. Here you go. I want, see here the black paper that you have right in here. Those papers are sold out there. If electric field mapping, lab experiment, Pasco sells some of those. Let's see if we have one here. Page field mapper kit. Let's take a look at this one. Here's the paper, see? We have a bunch of those papers right in here. And it's a kit that they sell. Complete kit, complete manual. They don't describe. Oh, here you go. Conductive paper. See that? With a grid. So those papers are sold out there. It has a grid. So you can locate the coordinates of this paper. The coordinates in the along within the paper. Okay. So P07. Here you go. We are going to use a special type of paper sold commercially that allow us to make measurements, to visualize. Let's see, Oni, looks like you're turning on your mic. Okay, I'm gonna turn it off again. I hear some background noise there. Thank you, Ani. Okay, this conductive, resistive / conductive paper has agreed in centimeters to locate the, let me, not to locate, but has agreed in centimeters that serves as a coordinate system for the paper, okay? And going back there, it's a shame they don't have the paper alone, but that's the paper here. Here you go. Let's try to zoom here. Yeah, do you see the grid here? The distance from each grid is 1 centimeter. They put those grids there so you can use it as a coordinate system. If you put the origin of a coordinate system here is 0, right? Here is 1, 2, 3, 4, 5 centimeters and so on. 1, 2, 3, 4, 5, and so on. Centimeters in the vertical or in the horizontal and vertical direction, right? Recall when we are playing with physics, you will always need to put a coordinate system, okay, in there. And that's the paper that I'm talking about. right in here, my first slide. That's how they sell these papers, with nothing there, just the black paper, nothing else. Okay, those papers are sold as a black paper with nothing else there. Nothing else there other than the grid painted throughout it. And then what else do we do? Once the instructor get those papers, so the instructor, once the instructor get this paper, what does he do? He paints, the instructor paints an electrode configuration, and by electrode I mean configuration that simulates different electric charge distributions. Okay? Once the instructor gets this paper, he paints an electrode configuration that simulates this electrode is painted with a pen that has a conductive ink. Okay? It's just your regular ink, but it has some flakes of metals there inside. This ink is conductive because it has some metal flakes throughout it. Sometimes it's nickel. The metal can be nickel. Metals, depending on the ink that you buy, right? Can be nickel, can be silver. Okay, I've seen nickel and silver out there, and that's the conductive pen that I'm talking about. You can buy that also. Here you go. It's a regular conduct. In this case here is silver ink. See that? Silver ink pen. But they also have conductive inks that they put nickel in there. And have you thought about that, making a pen like that of gold, Gold ink pen? Huh? I have never seen it, but you could, in principle, you could do it. Okay. I mentioned to you about the silver, right? The silver is the best conductor that we have out there. And they sell those things. You can look at the price tag there. Okay, and materials. Okay, we're going to use a special. I want conductive. Let's see, pen. I'm gonna pen made of a conductive ink. The metal can be either nickel or silver with flakes of nickel or silver. Okay. Once the instructor gets the above paper, right? The above paper, he paints an electrode configuration that simulates a different electric charge distributions using this conductive ink. Okay, here you go. Now you can erase it. Can you picture that? It's not difficult to visualize, right? Get the black paper, get your conductive pen, and then choose what electrode configuration you're going to use. In this case, in the case of this lab, the electrode configuration will be that of a two parallel plate And let's go back to here you go. And here you go. When I paint this paper, with the conductive ink, we end up with something like that. Here you go. You know, we have a metal film painted over this paper in a rectangular fashion, and another metal thin film, metallic thin film, which was originally our ink, painted in a rectangular fashion, right? So now my resistive paper or my conductive paper, right, has this thin surface, thin metallic surface, true thin metallic surface, okay? This surface is far more conductive than the conduction properties of the paper. That's why I like to call this paper resistive paper, okay? Because the students may mix it up. When you say a conductive paper, we assume that the conductive is very large, but it's not very large. The conduction of this paper is not very large. So much that this electrode has a conductivity far larger than the conductivity of the paper. Okay? Can you picture that? Okay, we didn't. Now that we have a paper with the electrodes, what we have to do? We have to charge those two electrodes. Okay, we have somehow to put positive and negative charges, positive charges in one electrode and negative charges in the other electrode. When we do that, we are going to create that configuration that we studied before. We're going to create the parallel plate configuration that we studied before. And as you already know, the parallel plate configuration is supposed to generate a uniform electric field between those two plates. Okay, 342. Are you following? But we didn't charge the electrode yet. We didn't charge the electrodes yet. Okay, we didn't charge the electrodes yet. So you go. Place resistive conductive paper on the top of the cork board. Okay, here you go. We're going to use a cork board. We're going to use a cork board to electrically insulate the resistive paper. And I'm gonna show you. Here you go. That's the cork board that I'm talking about. We buy this kit, right? The kit comes with the pen, the cork board, the paper, and some other things here that we're gonna cover very soon. And the cork board is a very good dielectric material. It's a very good electrical insulator. Okay. Next. Here you go. Insert 4 pins to the edges of the paper to secure it on the cork board. Those pins are metallic pins. So 4, here you go, 4 metallic pins to secure the paper over the cork board. Okay. And remember, I said that they are metallic pins. And the metallic pins are displayed right in here in your picture. 1, 2, let's see how many we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We put 10 in there. They don't need 10. We usually need only 6. 4 for the edges to secure the paper, and 2 for the electrodes. Okay. 4 metallic pins to secure the paper over the cork board. Let's go for the next one. Very soon I'm gonna have our break, okay? We'll try to cover as much as I can. Next, insert 1 metallic pin anywhere along the left electrode region. See, we're going to 4 metallic pins to secure, okay? 2 metallic pins punch it, right? At the position, right? At the position of each electrode. Can you picture that? One metallic pin here on the left electrode, another pin here on the right electrode, anywhere along the electrode. Don't forget, this is a highly conductive surface. Okay? This is a highly conductive surface. And 3:45, let's see if we can go another 5 minutes, right? So next, 6 pins, total of 6 pins. So let's write that down here. 6 metallic pins, okay? 4 to secure the paper over the corkboard, and 2 used at the position of each electrode, okay? So I made it simpler here. What's next? Now the plates are not electrically charged yet. And at this point in time, you should already know how electric charge an object, right? Here you go. Set power supply to 10 volts, okay? So here you go. We're going to use a power supply to electrically charge the electrodes on the paper, okay? So let's see if I can put out here also the procedure, right? So I can parallel the procedure with the materials. So 1, place your resistive paper with the electrodes over the cork board, right? Secure the edges of the paper, the 4 edges of the paper, with 4 of the pins, right? Insert 1 pin anywhere along each electrode, okay? Turn on the power supply and adjust it to 10 volts. And let me tell you what a power supply is. A power supply is nothing but a fancy battery, but a fancy battery. Okay, it is a battery that you can change its voltage, right? Everybody's familiar with the batteries, right? I showed to you my 1.5 volt battery, and a power supply is just like a fancy battery that you can adjust the voltage that you provide. And not only you have a 1.5 volt batteries, but we also have a 9 volt batteries, right? Your car has a 12 volt battery, and there are batteries also this 3 volts. There are batteries, all sorts of voltages out there. Let me show you how those power supplies look like. Let's see if we have here. Oh, here you go. Student power supply. That's one of possible power supplies that are sold out there. Okay? It's just like a box that you can adjust the voltage. See here, voltage here. V stands for voltage. A stands for ampere. We didn't cover ampere yet. Let's see if I can. Yeah, here you go. Here's the on-off power. Here you adjust the voltage. Here you adjust the current. DC power supply. And what you have right in here is just the negative and positive terminals of the power supply. This terminal provides positive charges. This other terminal here provides negative charges. And I have here my battery. If you remember, right, when I told you before, here you go. Here's my battery. Here's my battery. This top terminal here is the positive terminal, and this other one is the negative terminal of the battery. You have an accumulation of positive charges here at the top and an accumulation of negative charges here at the top. The power supply does the same, provides the same configuration, but it's a far more flexible device because it provides voltage, different voltage. Here's the switch on and off, power switch. Okay, so is 10:50 right now. Let's take our break so you can relax a little bit, right? Break from 10:51 a.m. to, let's see, 11:06 a.m., right? 11:06 a.m. So if you have any questions, do you have any questions before you go to the break? And we're going to use in the second lab, it's going to be exactly the same material, but just a different electrode configuration. So I'm going to walk you through very detailed so you understand how this experiment is performed, okay? So I see you in 15 minutes. See you. Thank you. Stop sharing. I am back here. Let me close the screen. Okay, so we're back. Let's continue with the procedure so you can understand how the whole thing works. And here you go. We have that power supply that I mentioned to you. You might not know what a power supply is, but you have seen the picture of one of them. And if you go in the internet, there are all sorts of power supply out there. The one that you saw there that I showed to you is just the one sold by Pasco, right? But there are others. This is one power supply. Let's take a look at other power supplies that are available out there. But they are basically a box that you can adjust the voltage, and the voltage is related to the energy, to the electrical energy. And then you have those terminals, the positive and negative terminals, power supplies. Here you go, different power supplies. Look at their value. They're displaying in Brazilian reais for some reason, okay? So this would correspond to $100 power supply. This one is $400 here. This is a larger power supply with more channels. This guy here has also, that's why it's more expensive, because it has more channels. Now, in reality, this guy here is 4 power supplies in a single box. That's why you have so many plugs here, okay? That's why you have so many plugs. See, one power supply here, another one, channel, right? Channel 1. Oh, it says only, channel 1 and channel 2. This one is just 2 channels. But I wonder why we have so many. Oh, that's okay. Let's skip that for now. Here you go. Another power supply. This one divided by 5, around $400. Okay. 32 volts. Do you see that? It goes to 32 volts. This other one is $100. Can go all the way up to 30 volts and so on. And DigiKey is one of the places that sell those things. Mauser too, okay? Let's take a look at DigiKey. This one is in the Brazilian website. I don't want the Brazilian website. I want the American website. Here you go. Let's take a look here. Yeah, here you go. DigiKey also sells. Why it doesn't do anything here? Okay, accept all cookies first. And power supply. Okay, AC/DC converters. Here you go. The thing that you have to charge your cell phone is a power supply too, okay? And power supplies are used in computers and so on. Some power supplies have fixed voltage, other power supplies has variable voltages. And what's going to be the next step? The next step, get a black cable. Okay, let's take a look at the black cable. It's the kit from Pasco. Let's go back to the kit from Pasco. Here you go. Kit. Okay, here you go. Field mapper kit. See that we have cables here, black and red cables. Okay, we're going to use that as well. So let's put that in the list of materials. One black cable and one red cable. Okay. The black cable is connected to the negative polarity. And the red one is connected to the positive polarity. So what do we do with those cables? Adjusted, well, 5. Connect the black, connect one end of the black cable to the negative terminal of the power supply. And the other end to the left electrode. Okay. Black cable and red cable. I'm going to say something else here, okay? With banana termination. There are all sorts of cables out there. Some of them have banana termination that are used exactly to connect to the power supply. Okay. With one banana termination and an alligator termination, like that. So one end has a plug, which is we call a banana termination. The banana termination goes exactly in the end of the power supply. If you saw the power supply here, you go to see it plugs exactly in those terminals of the power supply. Okay, and the alligator clip is just something that open and close. Okay, and what do you do? Connect one end of the black cable to the negative terminal of the power supply, and the other, that would be the banana plug. And the other end of to the left electrode, alligator clip. Okay. And here you go. That would be the next one. Here you go. I connected. Here you go. The alligator clip is connected right in here at this pin. Once you connect to the power supply, this plate becomes negatively charged. You do the same with the red cable, and you positively charge the other one. Okay, repeat. Here you go. Connect one end of the red cable to the positive terminal of the power supply, and the other end to the right electrode. Right electrode. Okay, and now the moment I do that, I have established an electric field here between those two plates. At this very moment, there are electric field lines running from the right electrode towards the left electrode, okay? We cannot see it, but you have to believe that there is something like that because we have an electric charge distribution here. We do have an electric field distribution as well. Okay? And in this case, the electric field is coming from the positive, going to the right one. What's next? What's next? Here you go. What you gotta do, set an imaginary axis connecting the middle of the two electrodes. That's what I tell my students when we are doing the experiment. Okay? Don't forget that we have that grid here that I didn't draw. I didn't draw the grid here. Would be too much work, okay? But here you go. That would be the origin of my x-axis. And then visualize the y-axis running on the left side. Here's going to be positive x, negative y. Positive x, positive y, right? Okay, as said, visualize imaginary x-axis running along the horizontal direction of the conductive paper, and a y-axis running along the vertical direction along the edge of the left electrode. Along the edge of the left electrode. The origin of this coordinate system is located in the middle of the left electrode. Next, here you go. Visualize an imaginary horizontal line connecting the upper edges of the electrode. Okay, let me copy that and paste there. And what else? Now we're going to use a multimeter. Let's digital multimeter is a standard instrument in any electronics lab, in any physics lab as well. So let's put it here. Okay, one black cable and one red cable with one banana termination. Each having one banana termination and an alligator termination. Okay, multimeter, digital multimeter DMM, digital MM, okay? And I have one digital multimeter here, I showed to you before, right? There are all sorts of digital multimeters out there. Digital multimeters are devices is a device that can measure voltage, current, Voltage and current. The simpler ones measure at least voltage and current. Then there are fancy ones that are going to measure other stuff as well, okay? And you can look at the internet to check the prices. Let's take a look here at this one. The prices of digital multimeter. Here you go. Here's the digital multimeter that Pasco sells. There are all sorts of digital multimeters, very similar to mine. Oh, it's the same brand name, by the way. X-Tech. See, that mine is X-Tech too, okay? Even the color is the same. Even the I didn't notice that. Isn't that cool? Just the keys of mine have more keys. Okay, but the rotating pointer here, select what you're measuring. That's what this pointer is done. This pointer is, you select what you're going to measure, voltage, current, or some other things, okay? Look at the terminals here. Let me see if I can, yeah, let's take a look. Look at the terminals. Red terminal for the positive, black terminal for the negative. This black terminal, red terminal is used to measure voltage, resistance, and other stuff, temperature as well, okay? These two other red terminals that you see right in here are for measuring current. Every multimeter has a separate circuit to measure voltage and current, okay? If you want to measure current, you use either one of those terminals here. If you want to measure voltage and other quantities, you use this red one right here. Okay. Just like mine, right? Just like mine. Let me. No, you're not going to purchase the power supply. No, you're not. Remember, this is not. Dana is asking whether you folks are going to purchase those equipment. No, you're not going to purchase this equipment. I'm just covering this material so you know how the experiment is done, okay? This is a make-believe experiment, right? And I'm just walking through how we perform this experiment. Ideally, right? You should be doing the experiment, ideally, but we do not have equipment to do that because it's an online class. So let's see here. And thank you for the question, Dana. Let me do something here. Oh yeah, that's right. You can do a simulation too. There are ways of doing that in a simulation. Yeah. Nice point. Good point, Quinn. There are ways to do simulations, and we're going to do that sometime. Okay. Let me see. I want to blur my. Yeah. Here you go. Here's my multimeter. Right. I want to measure voltage, so I use this red terminal and this black terminal right in here. And every multimeter comes with cables too. Okay, probes. See a probe, and that connects to the multimeter itself. If I want to measure voltage, I connect the red cable to the red terminal, and the black one to the black terminal in the multimeter. And now, with those two pointers, with those two probes, we measure the potential difference, the voltage. Okay, we measure the voltage. And don't forget, here you go, I have to adjust my multimeter to measure voltage DC. Okay. And let's go back here to my blurring. Okay. And now we are about to start the experiment. Here you go. Here's my digital multimeter. It's just another way, another digital multimeter that's available out there, right? With the terminals red and black. Here you go. All sorts of type of measurements, DC voltage. Okay. Omega here means resistance. And then what are we going to do in the next? So what we're going to do in this experiment? In this experiment, we are going to measure the different voltages between this plate and this other plate. That's what we're going to do. Okay, so let me write that down. We are ready to start the experiment. We didn't start the experiment yet. We are just setting it up. Okay, we are now, once you, let's see, connect the negative of the DMM, the negative probe of the DMM, right? To the negative electrode of the paper. Okay? Leave and leave and leave the positive probe of the DMM free to measure the voltage anywhere throughout the paper. Okay, and let me show you how we do that. Let's see here. Going back right here, the black cable of the multimeter is kept fixed right in here at this negative plate, and the red probe of the multimeter travels throughout this region here of the black paper. Okay, that's what it means. Leave the red one free and the black one attached to the negative polarity of the paper. That's what it means. And first, now we are about to start the experiment. But before starting the experiment, we want before we start the experiment, comma, we are going to check out the equipment. We are going to check out the equipment. That's the last step before we start the experiment, the checking out of the equipment, to make sure everything is working perfectly. Okay? Checking out of the equipment is something that we do in the lab. Even astronauts in orbit, before they launch a satellite, before they launch the space telescope, they do the checking out of the equipment before they let go their baby, right? The checking out is important to ensure that there is no problem with the equipment before we do the actual work. And there are very simple steps that we do in this experiment. The first thing that we can do, we can touch the red probe anywhere along the surface of this of the left electrode. Okay? Don't forget, the black probe of the multimeter is also here in the negative plate, in the negative electrode. So when we touch the positive, the red probe of the multimeter, we should get a 0 reading because there is no potential difference between those 2 points along this electrode. Okay? So here you go. Touch the red probe of the multimeter, of the DMM, anywhere along the negative electrode. You should read 0 volts. Okay? Another checking out. Then touch the red probe of the DMM anywhere along the positive electrodes. Here you go. That's the positive electrode. We get the red probe, touch anywhere along the positive electrode. And what should you read? You should read 10 volts. Okay. So anywhere along the positive electrode, you should read 10 volts. And now, let's see, do we have anything else to do? Let's see if we have anything else to do. Oh, touch also the pin, okay? Touch also the pin. Not just the electrode, but the pin as well. So let's touch the red probe anywhere along the positive electrode and the pin, right? And its pin. And here too. And its pin. Remember, the pin is a conductive material. It's made of a conductive material. Next. Read your voltage, right? It should be, okay, now we are ready to start the experiment. You read 0 volts here. You read 10 volts here. If you are not reading 10 volts here, or if you're not reading 0 volts here, there is something wrong with your setup, okay? But the next step is to get the data, and the data you already have. The data you already have, right? Remember the spreadsheet? Here you go, here's the spreadsheet. Do you see? I have 2 volts here, 4 volts here, 6 volts here, 8 volts here, 9 volts here, okay? What we are going to do, we are going to locate 1, 2, 3, 4, 5, 6 points that measure approximately 2 volts. 2 volts in the sheet, in the conductive paper. Not in the conductive paper, in the resistive paper. I like to call it the resistive paper. So what do? You slide your red probe of the multimeter along this line and find where you can measure 2 volts, okay? And once you find the place where you're measuring 2 volts, you should read the coordinate. Okay, should be 2 volts here. The coordinate, using the red probe, determine the coordinates of a 2 volt point along the x-axis. Okay. Let's copy that and place there. Okay, slide using the red probe, determine the coordinates of a 2 volt point along the x-axis. Okay. And that's going to be, here you go back to your spreadsheet, right? That's good. Along the x-axis, the y is equal to 0. See that? So here you go. Here is my point along the x-axis where I found a voltage. It's not exactly 2 volts. It's going to be 2.028. Okay? It's going to be 2.028. And you have to display it with the proper significant figures. And I'm going to show you how you find that out, okay? How you find that out. So you read the y coordinate and you read the x coordinate. Okay? And then what's next? Now is next one. Record the x, y coordinate in your spreadsheet, right? And they has already been done that. Here you go. Next. Record the voltage as well. Record the voltage and record determine the coordinates of a 2 volt point along the x-axis, comma, record the x and y values and the voltage read by the DMM. That's what we did. Next, here you go, this one here. Now we're going to find out the position of the 4 volt points along the x-axis. Repeat, here you go. Repeat repeat step 13 for 4 volts, 6 volts, 8 volts, and 9 volts. Okay. So let's make sure we have, okay, 2 volts, 4 volts, 6 volts, 8 volts, and 9 volts. Note that we're measuring just this one. All of them here has 0 volts. Double check that with your spreadsheet, okay? And then what you do next? You know, you start all over again. Find another 2-volt point, the location of another 2-volt point. You go. You know what I do? Tell my students to do. You go 2, 4, 6, 8, 9, right? Using the red probe, determine the coordinates of a second 2-volt point along the imaginary upper line. Okay? So let's copy that and paste that in my, using the red probe, determine the coordinates of a 2-volt point along the imaginary upper line. Record the X and Y value of the voltage read, X and Y values, and the voltage read by the DMM, right? Repeat, okay? For 4 volts, 6 volts, 8 volts, 9 volts. Okay, 4 volts, 6 volts, 8 volts, 9 volts. We see what we're doing? We're mapping the position within this paper of the voltages. Okay, and these surfaces and those points, you know, that have the same voltage, they make part of what we call the equipotential surface. We're going to do that for several of those points. He goes 6 positions, right? 6 different positions. Next, determine the coordinates of a third 1 volt, not 1 volts, a third 2 volts point above the imaginary upper line, right? Okay. And here, let me get that. I want to repeat step 15, right? Step 15 for the voltage for 4 volts, 6 volts, 8 volts, and 9 volts. Let's see, that's not what I want. I want something else here. I want this one here. Yeah, copy and paste it. Here you go. Determine the coordinates of a third 2-volt point. Now we're just repeating what we did before at different positions in the black paper. Above, but now above the imaginary upper line. Go as high as you can. Okay, record the X and Y values and the voltage read by the DMM. Like that. And here you go, more. 2, 4, 6, 8, 9, blah, 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 right? And I'll get 1, 2, 3. We have 3 more points to go. Okay. Determine the coordinate of 3 additional points with 2 volts between the x-axis and the imaginary upper line. Choose points that are evenly spaced along the y direction. We can copy that, right? Determine the coordinates of 3 additional points with 2 volts between the x-axis and the imaginary upper line. Choose points that are evenly spaced along the y direction. Okay, record their x and y coordinates. and their respective voltages read by the multimeter. Okay? And then you repeat for the other voltage, just like before. Do you see? Repeat. Let's see. I gotta put here, repeat here, right? Repeat step 17. I skip this one for 4, 6, 8, and 9 volts. Repeat step 19 for 4, 6, 8, and 9 volts. Okay? So here you go. And now you have all the points that you need for your spreadsheet. That's how my students collected this spreadsheet, these data points here, okay? That's how my students collect this. And now you should start working on that. Let's see what time is that. We should go another break, right? So we don't get burned out. 11:40 right now. Let's take a little break now and start looking at those data. You know, see, we have a voltage here. The voltage is not exactly 2 volts here, right? Because the multimeter, because it's very difficult to find the exact point with 2 volts. It's very difficult to find the exact point with 4 volts, and so on. Okay? All those values that you see here, they are not with the proper significant figures yet. Okay? For you that are doing my lab for the first time, all those values that you see right in here are not displayed in the proper, with the proper number of significant figures yet. And you will have to do that. You know, significant figures for the voltage, I'll tell you how you're going to get that. Significant figures for the x coordinate, significant figures for the y coordinate. Okay, according to that process that you saw. And by the way, there is one more equipment missing here of our list. Okay, we also need a ruler with a resolution. Resolution is the smallest division. Is a resolution of 1 millimeter. Okay, we need this other instrument here. Ruler is very important one. That's right. Okay. Repeat steps. Step 19 for 4, 6, 8, and 9 volts. Let's go another 3 minutes. Okay. Let's see. Any questions? It's lots of information, right? But that's how we do in the lab. I did this experiment so many times that I already memorized it. And I have all these notes, you know, all those illustrations showing the step-by-step procedure of your experiment, right? Here you go. Note, see that all those points, they kind of line up in a straight line. Do you see that? This 2 volts point here, they almost line up in a vertical line. Only when the points are outside this region here of the electrodes that they start to bend away from the straight line. Okay, that's exactly what we get. This straight line that you see here is a key configuration, is the key configuration of a uniform electric field. Okay, all those lines that you see here, we call it the equipotential lines or equipotential surfaces. Equipotential line of 2 volts, equipotential line of 4 volts, 6 volts, 8 volts, 9 volts. Okay? And we can find in a rough way the direction of the electric field right here. We can do that. Why is that? Because the electric field is always perpendicular to those equipotential lines or equipotential surfaces. Okay? If we're doing the experiment in a 3-dimensional volume, what you'll be seeing here, you'll be seeing a surface, an equipotential surface, a planar surface that extended up from the screen. of my computer, okay? So let's write it down here. For this specific experiment, here you go, 1 more minute to go before the break. You should get equipotential lines that are almost straight, okay, almost straight, and start curving just outside, just above the upper dashed line that connects the edges of the electrodes, okay? Connect the edges of the electrodes. This straight line, these lines of equipotential represent what you expect to get for a uniform electric field, okay? So let's take our break now. Okay, that is break 11:45. 11:45 a.m. to 12 noon. Okay. Any questions? I'm not missing any messages here, right? So let's go for our break. Okay, I'm back here. Okay, that's my notes. Okay, and now is that's when you get busy. Right now is the moment when you get busy. Okay, the first thing you're going to do, now data analysis. Okay, let's see. Equipotential, blah, blah, blah. That's the procedure, right? And that's still part of the procedure. Let's write it down like data analysis right now. That's first what you have to do. 1, plot the equipotentials using the data in your spreadsheet. And I'm going to walk you through how to do that, okay? It's not just like a regular X and Y graph. It's more than that. Okay, I want to walk you through and what we're going to do. Let's see. What are you going to do? What are you going to do? Okay, let's put going to do. 1, plot the equipotential, use the data in your spreadsheet. Next, what are you going to do next? Plot the P average versus along the y-axis, the y-axis, right? We're going to and and x average along the x-axis. Okay, so that 2 graphs, plot 2 graphs, plot 2 graphs. Okay, so here you go. Let me get something here first. Okay. I will walk you through how to plot the equipotentials, okay? And by the way, I gotta warn you about something else too, okay? Do not, by the way, do not change anything in the spreadsheet, okay? In the spreadsheet. Do not change anything in the spreadsheet. Do not delete lines. Do not delete lines. Delete lines. Do not delete cells, lines, or columns. Columns. Do not delete or insert any cells, lines, or columns in the spreadsheet, okay? Just leave it in this way it is organized. And like I said, you're going to plot the equipotentials, and you're also going to plot a graph, a second graph, okay? And I'm going to step you through, show to step by step how to do those plots. The equipotential is a little bit more complicated graph. It's not just like if you're already familiar with Excel, to plot the equipotential, there is a special technique that I'm going to teach you how to do that, okay? Here you go. Plot the equipotentials of the graph. What do you want to do with your graph? You want to obtain something like that, okay? That's what you want to get. You're going to get that data that you have with you, and you're going to generate a graph that's very similar to what you have right in here. Each of those crosses are just a data points, right? Each of them are just a data point. And how do you do that? We're going to plot the first equipotential. How are you going to do that? So here you go. First, you highlight the X and Y coordinates of the 2-volt data. How do you do that? Here you go. X and Y coordinates of the 2-volt data. Okay? Can you do that? Now it's time for your work. For now, you just listen to me, right? Now you're going to do some actual work. Everybody highlighted? Still have 45 minutes to go, right? So I'm going to call you randomly in case you're having any problems. Let's see. Delisha is not here, right? Mario Show is here. Let's see if Mario Show is here. No, I don't see Mario Show here. Ahmad? I don't see Ahmad either. Tatiana, is Tatiana here? Okay, I don't see Tatiana either. And I have one student trying to log in now. Good. Delisha is not here either, right? So I'm gonna call you one by one, just asking you whether you're ready, right? To here you go, downloaded spreadsheet. Yeah, spreadsheet. Okay, so how do I highlight? All you have to do, Susan, all you have to do is get your mouse here. Here's the cursor. See the cursor here? Hover your cursor over this point here. Left click, okay, and drag. See, I'm highlighting the X data in the vertical column, and then move to the right so you can highlight the X and Y, okay? Did you get it? Did you get it, Susan? Okay, thanks. Okay, so here you go. I'm gonna keep on switching back and forth because I have you highlight the X and Y coordinates of the 2-volt data, right? And then what do you do? Next. Leave it highlighted. Click Insert at the top of the spreadsheet, right? Highlighted. Go here, Insert. See that? It is as though we are plotting X and Y chart. And then what do? You go to the chart region, and you want to plot a scatter plot. There is an arrow down, highlight the arrow down, and highlight this one right here. Do not highlight this one, do not highlight this one. This one with no lines whatsoever, okay? That's your first equipotential, okay? And what do you do? Click insert, okay? Click OK. Click insert, go to charts and click insert scattered. Choose the very first scatter plot with no lines connecting the point, click OK. And click OK. You plot your first equipotential. Okay, you plotted your first equipotential. Next, plot the second equipotential. It doesn't look like a straight line because there's a reason why it doesn't look like a straight line, okay? You do exactly the same thing that you did before. You highlight the X and Y coordinates of the 4-volt data, right? No, sorry. There's one step before that. Let me fix that. Click on, yeah, there's one step before that. Here you go. Click on the data points of the graph. One of the data points of the graph, okay? Let me show you how I do that. Here you go. Here's my graph. Here's my first equipotential. It doesn't look like a straight line, and there's a reason for that, okay? The reason it doesn't look like a straight line because of those coordinates here. They're too close to each other, but you are going to start to see the equipotential once I plot the next set of data. So what do you do next? Click one of the data points in your graph, okay? When I click one of the data points, all the data points are highlighted. After clicking one of the data points, you right-click while it is highlighted. And then we get this drop-down menu, okay? And we go to Add Data Labels. Okay, wait a minute, no, sorry. Select Data, not Add Data Labels. Add is gonna come next. When you highlight Select, okay, select Data, this window is gonna show up. Series 1 is the first set of points that you plotted there at 2 volts. But now we are going to add another option right here. We're going to add another set of data points. The next set of data points are going to be called 4 volts. Okay? And make sure also when you do that, make sure you move your chart away from the table. Okay? Right now, my chart is between me and the table, and I cannot locate the proper points to plot. So what I'm going to do? I'm going to cancel that for now, okay? I'm going to cancel for now, and I'm going to move this chart right here, and now I can work again, okay? So here you go. Click one of the data points. Am I going slow enough? Right-click it, select data. I'm going to write that down, all that for you. Add, and now 4 volts, right? 4 volts equipotential, highlight those 2 columns. Let's see. No. Highlight this one first. Highlight this one first. That's the X values. And then click on the Y values right in here. Why it doesn't do that? Yeah, here you go. Take away this number 1, okay? And highlight the Y column. Do you see what we're doing? We are telling Excel to plot this here along the x-axis and this set of data along the y-axis. Okay, that's what we're doing here. I right-click and nothing happens. Are you using a Mac or a Windows computer, Susan? Ah, okay. Mac works differently. Okay, Mac works differently. There are other ways of doing that. Sometimes Mac works exactly like a Windows computer. Sometimes it doesn't. Let me think about that. But let me click OK first. Okay, here you go. And now you're going to see the first 2 volts and the 4 volts, right? Equipotential. Susan, see if you can see anything like that I have here. I believe it's right in here. Let's see. That's filter, right? Oh yeah, it should be here. This funnel that you see right in here. Okay. Do you see those 3 boxes on the right side, upper right corner of your graph? Max, we usually display that. No, don't see that. Okay. Let's see. So if you click it, and yeah, it looks like we have to do that during the. Oh, you can switch computer. Okay, if you can switch computers, it would be great. Okay, there's a way to do that with the Mac. I just don't remember right now, but I know that there is a way to do that with the Mac. If you can switch the computers, then it would be great. Okay. So do you see now that we have 2 equipotential curves, right? Or 2 equipotential lines. This is the 2 volts. This one is the 4 volts. And my electrode is right in here. It doesn't show, but it's right in here. My half electrode, right, is right in here in the extreme right. And I am going to copy and paste what I just did it. So you have the instructions, second equipotential right here. Let's see, plot second equipotential, plot the remaining equipotentials using the instructions in the B item, right? Item above. Once you do the second equipotential, you can do the third, the second, the third, the fourth, and the fifth. Okay? 6, 8, and 9. So let's go do the rest. Click one of the data points, right click it, right? You press on the graph, and at the top of the screen, you will find select data. Oh, okay, good. You have a Macintosh, Nadia? Okay, yeah, here you go. See, Susan? Nadia figured out how to do that. That's good. Thank you very much, Nadia. Thank you. You know, I get students with Macintoshes, I get students with Windows, I get students with the Chrome. The Chrome is the worst of them. You know, the Chrome doesn't have all the possibilities that the other computers have. So here you go. I'm going to left click, right click, select data, add, and now it's going to be 6 volts. Oh gosh. Edit. Okay, here you go. 6 volts. Yo. Be careful with the back, with the arrows. Okay. Yeah. Okay, leave like that. Highlight the X value. Oh, what happened here? Let me do all over again. Series name 6 volts, right? No, make sure you have included all the required parentheses and arguments. Okay, don't need a parenthesis and argument, do you? Do you? What's going on here? 6 volts. Let's see. Yeah, okay. I put the equal sign here. It doesn't accept the equal sign. Series X volts. Now we want highlight 6 volts, the X values of the 6 volts. Okay. And it basically he gets the coordinates of those points and he type it here. See that? M9 to M14, right? This is the column M. Here is the row 9 all the way down to row 14. That's what it's doing. Go to the Y value, erase what you have here, and highlight the Y values. Click OK, okay? And click OK to see your masterpiece, right? Here you go. Well, we are in the process of creating a masterpiece, 2, 4, 6 volts. You're not done yet. Note that this group of students here, they didn't follow my instructions, right? Here's the upper edge of the electrodes. Here's outside the upper edge of the electrode. I told them to get those 3 data points evenly spaced, but they didn't. They concentrate the data points in this region instead of spreading them out evenly throughout this line when they're collecting the data, right? But that's okay. That's okay. You know, 2, 4, 6. Next is 8 volts. Left click, right click, select data, 8 volts, right? Click OK. Oops, what did I do here?
So, Professor, as we're plotting the points, it's okay. You're saying if the points aren't linear?
Yeah, it's okay. See, they're a little bit inclined. Okay.
Right. Okay.
But they shouldn't be too much off. Okay.
No. They're not off. They're just slightly off. Not
Yeah,
off.
they're just a little bit inclined. You're going to see that
Okay.
they're almost lined up.
Yeah, they're almost linear.
Yeah. Okay. So let's do it again. Right click, select data, add. I need to do the add. I forgot to do the add. Right, here you go. Now I type 8 volts. Okay, remember, as you do that for the first time, you're going to make some mistakes along the way, right? So just be patient. Then you follow the instructions and you will eventually get everything right. What says 8? Here you go. Y. Okay, and now I have my next set of data points. Okay, here you go. Okay. Now, do you see that the equipotential lines are starting to veer to the right? Here they were a little bit to the left, a little bit to the left, right? A little bit to the left, but this one now is veering a little bit to the right. Why is that? There's a reason for that. They're veering a little bit to the right because the right electrode is closer to the set of data points compared to the left side of the electrode. The electrode tends to, let's say, attract the equipotential lines towards it. And the closest the electrode is, the more of an inclination you're going to get in the plot. So 2, 4, 6, 8. One more, the last equipotential. 5, 12, 23. You still have what? 45 minutes to go? Okay. So left click, right click, select data, add. Now it's going to be 9 volts. Okay. X value, click here on X value, and then highlight the set of X value data points. Erase completely where it comes next, and highlight the Y value in the column. Click OK, and we should get our last equipotential. Okay? Note, see that those two equipotentials are closer to each other. Why is that? There is a reason for that. Okay, there's a reason for that. Type there in the chat window if you know, or if you guess, if you think you know. I'm going to write that down here in my notes. When you plot when you plot the 2 volts, 4 volts, 6 volts, 8 volts, and 9 volts equipotentials, the 8 and 9 volts set equipotentials will be closer to each other compared to the remaining ones. Why is that? Remaining ones. Why is that? Okay. I'm going to illustrate that for you again. Here you go. Here are my equipotentials. Those two are closer than those two, right? Then those two. Then those two. Why is that? There's a reason for that. I want you to think about, let's see, KM, Kimberly, because the votes. Yeah, that's right. That's right, Kimberly. Here is 2 to 4, right? It's 2 volts difference. Here is 4 to 6, 2 volts difference. 6 to 8, 2 volts difference. And here's just 1 volt difference. Because the electric field is uniform, the spacing between the voltages should be the same. But because, we have 2 volts difference in the other ones and just 1 volt difference between those two, they should be closer compared to the other one. Okay? That's right, Kimberly. So we got our first one. That's what this equipotential should look like. Doesn't it look like the one I showed to you before? Right? Let's see. Right in here you go. See that? Somewhat, right? Bending towards the closer electrode, bending towards the closer electrodes, right? Here too, bending towards the closer electrodes, right? They're almost the same. And the electrodes should be right in here at the x equal to 0. Okay. The other electrode, well, we do not know. Should be maybe around here. The other electrode should be around here at the same distance than the 8 volt electrode, than the 8 volt equipotential. Okay, so now you have to make this graph look nice. Okay, gotta make this axis look nice, this graph look nice. Don't leave this way, okay? Work a little bit on that. Label the axis and change the numeric type. Use font 14 for the numbers along the X and Y axis. Use font 16 for the labels of the X and Y axis, right? So here you go. Here's my graph. Equipotential, right? I don't like to keep a chart here. I usually erase it from here. And now we are going to work out on the axis. Okay, so right in here, I'm going to change the format of those numbers. Double click on the axis, on the labels of the axis, okay? And then you gotta look for number right in here. Do you see the category? Right now, my category is on scientific. I don't want scientific because sometimes scientific is difficult to read. I'm gonna put it as a numeric value, number. Oops, but then I have to put some decimal places there too, right? Let's see, let's put one decimal place. Let's see if we can see everything. No, we cannot see everything. We have to put 2 decimal places, okay? And now we have 0.01. That's all in meters, by the way, all in meters. 0.01 meters is 1 centimeters. 0.02 meters is 2 centimeters, and so on, right? We do the same for the x-axis, for the labels of the x-axis. Here you go. Number, scientific, you change numeric, but then you increase the decimal places to 2. Yeah, 0, 5, 10 centimeters, 15 centimeters, 20 centimeters, and so on, right? We're not done yet. We're not done yet. You know, when you do all of that, I'm going to correct all of it, okay? I'm going to give you a grade for that. What else? What's the size of those fonts? Let's take a look at the size of those fonts. 9, okay? Here you go. The size of the font is 9. Oops. So increase the size from 9 to, hey, where is the, yow. Okay, so let's see here. Numbers, tick labels, no, tick marks, no number. Let's see, maybe it's here. No, where is the format for that? Let's see, where's the format for that? It was here before. Home, oh, okay, here you go. Yeah, you gotta click on home. Home tells you what the font and the font size, right? What I suggest to my students to use font size 14. Otherwise, it's gonna be difficult for me to read that. Remember, I'll be correcting it here. Here you go. Right? And do the same 14 font size here. When you write a scientific paper, you have to do all of that, okay? Make it look nice for publications. You don't want to publish a crappy graph, right? That everybody's gonna have access to. Okay, so now what's missing? The labels of the axis is missing. Here's the x-axis and here's the y-axis, right? So the label of the x-axis, how do you get it? Click the chart, chart design. Okay, here you go. I'm gonna do that again. Click the chart. Notice that when I unclick the chart, when I click the chart, 2 other options appear here at the top, right? Take a look. See? Chart design and format shows up. I'm going to unclick. Chart design and format disappeared. Reappears. Okay? When I click chart design, then you have all those options here. The option that you want is the chart element. Add a chart element. Click the arrow down. Let's see, chart title, no, axis title. Is the axis title that you want. Primary horizontal. And now, see that? He created a box that you can type the name of this axis. And we are going to do the same for the y-axis. Axis title, primary vertical. Okay? What you're going to do here? You're going to type X, open parentheses with the unit. Always put that. I spelled that out in my syllabus, okay? Bold-face it. Bold-face it and increase the size to 16. The numbers are size 14. The label is 16. And you do the same right in here. Type Y parentheses meter, right? Highlight everything, bold face, size 16. Okay. If you want to, here you go. Professor, can we get the steps to do live after Zoom? Yeah. Yeah. I am, let's see here. It's, by the way, it's in the syllabus, okay? Let me see here. You're talking about the steps written down in the notes. That's what you're asking, Susan? Okay. Let's see. I think I have. Okay, here you go. Label the axis and change the numeric type. Let me see if I can copy and paste here. Oh yeah, I did it. Label the axis and change the numeric type. Okay. Let's see what I'm gonna do. Write it down here. One, go. Double click along the in the numbers along the x-axis, right? That's what I did. A panel should show up at the right side. Okay. Here you go. Let's go back there. Double click, the panel shows up, right? The first thing that you're going to do is go to number. Click number. Click number at the bottom of the panel. Okay. Oops. Going back there. Click number and make sure, it should be showing scientific notation here, right? Change the category to number. Okay. Here you go. Change the category to number. Change the category to number. Okay. Change the category to number. What else? Yeah. Okay. So we changed to number. This is the way we want. And then you want next. What do you want to do? You want to change the size of those numbers, right? Click the numbers again along the x-axis. Click the numbers along the x-axis again, and at the top of the screen, at the top left of the screen, top left of your screen, select home, right? Select home. Select home. When you select home, you'll be able to see the font type. Here you go, the font sizes and type. Here you go, home. Now, this guy here has this font type and this font size. Look for the font size, right? Look for the font size at the top, right? Look at the font size. At the font size at the top of the screen and select size 14. Okay, that's what I did. Now, repeat above for the y-axis. Okay. Repeat above. Okay. Label the axis. Label. Okay, label it. Let's see. No, it's not label the axis. We are going to, yeah, label the axis and change the numeric type. Change the numeric type to numbers. Number. Now, what's next? 2. What would they call it here? Let's see here. What they call it here is here. No, let's see here. Chart design. Yeah, add chart element. Okay. Okay, how do we call it? Let's see, let's go back there. I want to use the proper wording that's used here in the axis title. Axis title, okay? Add title to the axis, right? 1, click anywhere in the graph, right? That's what I did. Make sure you select the graph. What time is that? 5:40 already, and we have 10 more minutes to go. Here you go. Click the chart, okay? When you click the chart, chart design is going to appear there at the top. Click at the chart. We're running out of time. Let's see if we can finish that. Add title to that. Select the chart, okay? Select the chart. Choose chart. Type will appear at the top. Will appear at the top. No, chart design will appear at the top. Will appear chart design will appear at the top right. Okay. Chart design. Click chart design. If it's already click it. Click chart design. Okay. What else? Here you go. Add chart element should appear at the extreme top left. Extreme left at the top. Add chart element. Add chart element should appear at the extreme left at the top of the screen. Okay. Okay, next. Oh, I keep on doing the same thing here. Oh boy. Here you go. Select add chart element. Click on add chart element. Click. Add chart element. Okay. A drop down menu should show up. Here you go. Should show up. Here you go. Select axis title. Select axis title. Select axis title and add the title for the X and Y axis. Okay. Select font size 16. Select font size 16 for the titles of the X and Y axis. That's what I did. And bold-face it too. I like it bold-faced and bold-faced as well. Okay. So 44, we have 6 more minutes to go. Doesn't look like we'll be able to finish today, but that's common. Okay, we don't usually finish the first lab in one day. We will continue, next time. Okay. But let's do as much as we can. Let's take advantage of those 5 minutes that are left over. And I didn't. I remember I didn't cover everything. I want to be able to cover everything that you need to do for this lab. Okay, but we are covering enough. Let's see. Select font size 16. Okay, looks like. Okay, so we got our equipotentials here. We got our equipotentials here. Okay. And if we go back to my PowerPoint slide presentation, right? Once you get those equipotentials here, what is going to happen? What you're going to do? You're going to draw a line through those curves, an average line. Okay? And those are the equipotential curves, like I mentioned. And what else you're going to do? You're going to draw vectorial lines, okay, electric field lines that are perpendicular to those equipotential lines, okay? See that? The electric field comes out from the positively charged electrode, passes through those equipotential lines perpendicular to the line, perpendicular here, normal, right? Normal here, here too, normal, see that? Because the equipotential is curving, the electric field lines are going to curve as well. And that's how you find the direction of the electric field lines. You find the direction of the electric field lines from the configuration of the equipotentials. From the configuration of the equipotentials. Okay? And the electric field lines are always, I don't say perpendicular, I say normal to the equipotential surfaces. In this case, it's the equipotential lines. Let's write it down. We have 3 more minutes to go. I have, okay. After you plot the equipotential lines, draw an average line connecting each equipotential separately, okay? Separately. These are the equipotential surfaces or equipotential lines or surfaces. Okay? From those equipotential lines or surfaces, draw the electric field normal to these equipotential lines. Equipotential lines. Okay? Normal means perpendicular to the tangent direction. Okay? This exercise allows you to visualize the genetic behavior of the electric field. Okay, so we made measurement of the equipotential, right? Values. From the potential values, we determine the electric field, the direction of the electric field. One more minute to go. Any questions? I hope I documented everything here, right? This one is just our first graph. The first graph takes a long time to do because the first graph is actually a total of 6 graphs, right? 1 graph, 2 graphs, 3 graphs, 4 graphs, oh, 5. 5 graphs. The total of 5 graphs. 5 graphs in one. Okay? The next thing that you have to do, you're going to plot table, we're going to use table 1.2. You're going to plot the average versus x average. That's the second graph you're going to do. And we're going to do that next time that we meet next week, okay? So there is no lab report due next week because we didn't finish this one. We should be able to finish next week. And then you should turn in the lab report after, 2 weeks from now. Okay, so we can stop now. I have office hours right now. If you want to stay around to talk to me and need help, just hang in there. Okay? See you next week.
Thank you, Professor.
See you.
Thank you.
Thank you, Professor.
Thank you.
Welcome.
I have a question.
Yeah?
So looking at the table, you want us to plot each number?
Are you talking about this graph here?
Yeah, well, the spreadsheet that you gave me, my partner, you would like us to plot each number on the table.
Each number in the table. Okay, you got a spreadsheet with all those numbers, right, Oni?
Right.
Okay, you have all those. Did you plot this graph here?
Oh no, not yet. I'm asking like.
Yeah. You're supposed to plot this graph here. Okay, I was walking you through in detail how to plot this graph because it's not easy to plot it. Okay.
Right.
You should have followed my step-by-step directions to plot this graph. Yeah, you have to plot this graph, but we can do it next time. We can do next week, okay? Or you can try to do that on your own as well between now and next week.
Okay. No, I was watching what you were doing. I just wanted to ask, like, is it good? You look at the table and you plot each.
Yeah,
one.
you gotta plot each one. Plot this one, then plot this one, then plot this one. Okay, that's what you have to do. Plot this one, and plot this one in a single graph. That's what you're supposed to do. Okay.
Use different colors or.
Huh?
Do we use different colors or?
Oh, yeah. Excel does that automatically for you. See that? Those are blue, right? Those are kind of brown. This one is green, right? See, Excel does all of that automatically for you.
Oh, okay.
Okay.
Okay, thank you.
Welcome.
All right.
Anybody else need help?
Yes, Professor. I was following along, but I'm having a problem. I have a Mac, and I'm having an issue I guess getting the numerical values
Uh-huh.
on the chart, you know, the 0.00 to the 0.09.
0 point, are you talking about what, the axis? Are you, what are
Yeah,
you talking about?
the axes, like I'm having a hard time
Okay,
trying to do.
so why don't you share your screen with me, and so I can
Oh,
visualize what's going on there. Okay, so here you go. Go ahead.
that's the thing. Hold
Do you know how to
on.
share the screen?
I'm on my computer, but I'm on my cell phone, so I can't share my screen.
Okay, so I cannot see your screen, you know. Can you log in through the computer?
I can.
If you log in
Let's see.
into Zoom through your computer, you'll be able to share your screen with me.
Okay, let me go ahead and do that.
Professor, did we take roll today?
No, I didn't take row. There's no need to take row.
Okay.
Okay,
Okay, thank you.
okay.
Have a
Okay, you're logging through your computer now, right, Dana?
Yes.
Okay, now share your screen with me, please.
Where do I go? Oh,
Okay,
more.
you go to the top, to the middle bottom of the screen. There is a share box, is a green box. Okay, it's a green box written share at the bottom of this green box.
Oh, got it.
Okay, it's coming. Okay, now show me the plot. Okay, did you download this spreadsheet to your hard drive?
Yes.
Okay, and so show me where the spreadsheet is in your hard drive, please.
Mm,
You
how
should
would I
be
find
able.
that?
It should be in
Because
the download
I
folder. Should
yeah,
be.
it's in my download folder, but I'm using the Excel through school, if that makes a difference.
It looks like you're in the cloud. That's why I'm asking that. You
Yeah, I'm not really sure.
yeah, it looks. But let's see. Let's see. Double click do you see the zeros there at the bottom?
Yes.
Double click there. Okay. Well, what was your problem that you told me you're
The
having?
numerical values is, do I go here?
No, no, no. Go down. Let's see. Let's see. Go down. Font. Where is the category? Series. Go up. Go up. Go up. Let's see here. Go click data. Data at the top. Let's see what's going on. Your, it's showed differently. Let's see. Format. Click format again. I'm suspecting that, let's see, units, go down. It has, I'm suspecting that your number four, oh yeah, here you go. Number format. See that at the bottom? Number format at the
Number for
bottom.
uh-huh. Uh-huh.
Category, number. So you have it number. Now
Yes.
decimal places. Yeah, here you go. You're good. Now put decimal places there. Put 2 decimal places. Instead of 0, put 2. Okay, now get out of that box. Yeah, see that? Now the number switched to 2 decimal
Mm,
places. See that? Let's see
okay.
if we can change the font size as well. I think I saw font size there. See because you're a Mac,
Yes.
right? Your Mac is different. Go down, go further down. I think I saw font size there. Oh yeah, see that font, Calibri, size 14. Good. Yeah. Okay, so you have everything in the pane. My computer doesn't have all that stuff in the pane, right? So it's slightly different.
Okay.
Then you do the same for the vertical axis. You do the same for the vertical
Okay.
axis. You double click
Oh,
the numbers in the vertical axis.
where's
Move to the left. Move to the left.
uh-huh.
See
Oh, okay, okay.
the numbers in the vertical axis. Double click there. Oh, can you do that? Ah, that's another way. Okay. Decimal places, 2. 14. No, put 14, don't put 16. 16 is the other. Okay, now click outside. Yeah, okay, see that? Now you have it.
Mhm.
The number is the
Mhm.
right decimal places, right?
Right. Okay. That was all. I was a little confused on that.
Okay, so unclick the graph. Unclick the graph. Click outside the graph. Okay, now click back in the graph again, in the chart again. Yeah, click there in the chart at the top. Let's see if we have. Do you see the chart there at the top that's highlighted?
This?
No, at the top. Go top. No, do you see top left file? Do you see top left file?
Yes.
Okay, home, insert, share, right? All the way
Yes.
down, you have chart here. Make sure the
Yes.
chart is okay. Okay. See access title now? Access title below automate and help. Go to the left.
Access title. Correct.
Yeah,
Got it.
here you go. Access title. Click there. Primary, see that? It's arranged differently from mine, okay? Horizontal axis title. Let's see. Title below axis. Select title below axis. More to the right. More to the right. Yeah, here you go. Now write it down. X, letter X, open parentheses. Clock M, put M for meter. Close parentheses. Put a space between the X and the open parentheses. Yeah, now click OK. Now let's take a look. See that the X is very small, right? So now we have
Yes.
to change the size. Right click it. See if we can get the okay. Yeah, put now you put 16. Yeah, boldface, good. Boldface and put size 16. Do you see the number 10 next to Calibri?
It's not
Yeah,
bold,
16.
so
Good.
okay.
Yeah.
Now bold.
And you do the same for the y-axis. Okay,
Okay.
axis title. See, it's completely different from the configuration that I have,
Yeah, I see.
but if you know, but if you break your head enough that now it's not X. This one is Y, right?
Oh,
Y
why?
parentheses. Y open parentheses. Yeah, and put meter there. Good. Click OK. Man, it's so different. Oh, but it put in the vertical direction is so bad. Let's see. There's a way to fix that. Let's see. There's a way to fix that. Erase that. Delete that. There's a way to fix that. Good. Go back in the X title. Let's see. Primary vertical axis, right? Now, go step by step. See that? Non-rotate title, vertical title, horizontal title. Let's see how display axis title horizontally and resize chart. Vertical title, display axis title with vertical text. Yeah, you want the vertical title. Vertical title. Yeah, now you repeat what you did. Yeah, good. Let's see how it looks like now. No. Okay, we have to choose the other one. We have to choose the one. We did that again. Yeah, we have to choose the
Okay.
one. Yeah, that's axis, primary vertical. Is that rotate title? Yeah, the rotate title. That's what we want. We want rotate title. Now, let's see if that's what we want. Yeah, that's what we
Got it.
want. Now we have to change the size, bold face. Okay. Yeah, good. Now you know how to do that, right?
Yes, got it. Got it. Thank
Yeah,
you.
it's completely different than what I'm displaying here in mine. Must be because
Okay.
the version of the Excel. Uh-huh.
Okay. Yeah, that was all, Professor. Thank you so much.
Welcome.
All right. I'll see you on Monday.
What's that?
I'll see you on Monday. Thank you.
Okay, see you, mother. Bye-bye.